What if I told you NASA just fired a prototype engine that could change the way humans travel to Mars? Not a giant chemical rocket, not the kind of engine that burns for a few minutes and then goes silent. This one is electric. It feeds lithium metal into a plasma chamber, pushes current through it, and uses magnetic forces to throw that plasma out the back. And in February 2026, inside a special test chamber at NASA's Jet Propulsion Laboratory, it reached something important: up to 120 kilowatts. That number sounds technical, but here is why it matters. The electric thrusters flying on NASA's Psyche spacecraft are already extremely powerful for a real spacecraft. This new JPL test reached more than 25 times that power level. That does not mean we are launching astronauts with it tomorrow, but it does mean NASA is testing the kind of propulsion that could one day move massive cargo, deep space spacecraft, and eventually human Mars vehicles with far less propellant than traditional rockets. To understand why, compare two very different ways of moving through space. A chemical rocket is like an explosion you control. It produces enormous thrust quickly. That is what you need to escape Earth. Electric propulsion is different. It produces a much gentler push, but it can keep pushing for a very long time. In space, that steady push can build huge speed over weeks and months. The problem is scale. Most electric thrusters are efficient, but relatively low power. Great for robotic probes, not enough for the huge payloads you would want for a serious human Mars architecture. That is where this lithium-fed magnetoplasmadynamic thruster becomes interesting. Instead of using the electric field design found in many ion engines, an MPD thruster uses high currents and magnetic fields to accelerate plasma directly. In simple terms, the engine turns electrical power into a fast, directed stream of charged particles. The JPL team fired the prototype 5 times. During those ignitions, the tungsten electrode in the center glowed bright white, reaching more than 5,000 degrees Fahrenheit. The plume was not just a visual effect, it was the point of the test. Can the hardware handle extremely hot lithium plasma at very high electric power? That is why the test happened inside a special JPL vacuum facility built for metal vapor propellants, high-temperature components, and future megawatt-class electric propulsion. Now, the bigger target is much more ambitious. NASA says the team wants to push toward 500 kilowatts to 1 megawatt per thruster in the coming years. For a human Mars mission, the total propulsion system could need 2 to 4 megawatts of power, which means several thrusters operating together, most likely paired with a nuclear electric power source. That is the real idea. Chemical rockets still launch you from Earth, but once a spacecraft is already in space, a nuclear electric system could run powerful electric thrusters for months, using propellant far more efficiently. Less propellant can mean more useful payload: habitats, supplies, shielding, scientific equipment, and hardware needed to keep people alive far from Earth. But the difficult part is not making a dramatic plume for a few seconds. The difficult part is endurance. A Mars-class system may need thrusters that operate for more than 23,000 hours. That is years of accumulated operating time while hot electrodes, plasma, metal vapor, and extreme currents attack the hardware. So this is not a finished Mars engine. It is an early but serious step on a long engineering road. The test showed that the prototype works at the targeted power level. The next question is whether the components can survive repeated tests, longer firings, higher power, and eventually the reliability that human exploration demands. Mars is not just about building a bigger rocket. The hard part is building an entire transportation system: power, propulsion, cargo, timing, life support, radiation protection, and the ability to move heavy things across the solar system. If NASA and its partners can scale it from 120 kilowatts to megawatts, this technology could become one of the engines behind the next era of deep space travel. So yes, be skeptical. One test does not make a Mars spaceship, but do not ignore it either, because the path to Mars will not be built from one spectacular launch alone. It will be built from technologies like this: hot, difficult, extremely technical, and easy to miss. And sometimes, the future of human spaceflight begins as a red plume inside a vacuum chamber in Pasadena.